We have seen that the laws of Newtonian mechanics are unchanged under Galilean transformations. The next question is, what about the electrodynamics of Maxwell, whose outlines we recalled during the last lecture? So this is the subject of lecture 3, and I draw your attention to the corresponding notes starting at page number 13. Again, we consider two reference frames S and S prime, both inertial frames, and S prime is moving with respect to x in the positive x direction with velocity v. Now, we start by postulating that Galilean transformation from S to S prime does keep Maxwell's equations invariant. Before we go to Maxwell's equations per se, let us consider a charge and consider the force on it from either frame. If Galilean transformation is valid, then the force on a charge, component-wise, must be the same in both the frames in whatever direction the charge moves. Let us consider the figure in the lower part of page 13. In the frame S, there is an electric field along the y direction, a magnetic field B along the z direction, and a charge, very small charge Q, moving with velocity small v along the x-axis. When you go to frame S prime, the same charge is seen to move with velocity v prime, and the values of E and B becomes E prime and B prime respectively. Now, E prime and B prime are kept in the same direction as E and B prima facie, because otherwise the force on a charge would be different in the different two frames. And in that case, to start with, we will lose Galilean invariance. And other components don't build up, because then a charge moving in a different direction in frame S, not in along X, will also develop components of forces which do not exist in frame S. Keeping all this in mind, the figures in page 13, lower part, are written, and component wise, there being same force on both the frames on the charge, one can write what is called equation 38. You should remember something here. The charge is assumed to be tiny compared to what could have changed B or E in either frame because of its presence. In other words, B and E are assumed to exist irrespectively of the charge, and the motion of the charge does not modify B and E in any significant manner, so small the charge is. So having seen equation 38, and remember the relative minus sign between the E and B terms, because there's a negative sign coming in as V cross B is along the negative Y direction. After this, just with some simple algebra as done in equation 14, you can see that a transformation prescription for E as well as B follows, as given in equation 41. This is very straightforward algebra. This then should be the way E and B transform in such a case in the Galilean scheme. We are so far still retaining the hope of having similar electrodynamics in both the frames under Galilean transformations. Now let's take up Maxwell's equation. Let EB and E prime B prime in a specific example, remember this is an example, not a general proof, is let them be coordinate dependent, but both being functions of x only and also of time. But they are not functions of y and z. In such a configuration, we will show whatever we need to show, and then we will move from there. Now, take the limit where j equal to 0 at some point in space, that is to say, a charge-free point in space. Then the last of the Maxwell's equations, curl B equals mu naught epsilon naught del E del T, is considered. In this example, keeping the prescriptions of taking curl, etc. in mind, we can reduce this following the steps given very clearly in the subsequent equations. We arrive at equation 45, which is the way this equation curl B equal to mu naught epsilon naught del E del T, the way it behaves. And we also make use of the relationship mu naught epsilon naught equals 1 over c squared in the SI units. Now, the equation 45 will be gradually step by step examined in terms of the variables in frame S prime, because that is our purpose, to see how the equation looks in terms of the transformed variables. Now it is straightforward algebra. There is no point just reading out the steps. Del B del X and del E del T are transformed using the usual chain rules, and we also apply x prime equals x minus vt, t prime equals t, because still we are under the spell of Galilean transformation, and we are assuming that time flows in identical manner in both the frames. Thus we proceed and obtain equation 48. Then we try to express E and B in terms of E prime and B prime following equation 41. Again follows a little bit of algebra, nothing special, from which we obtain equation 50, and then equation 45 takes the following form in terms of everything in S prime, a form which is given in equation 51. These follow with no physics, just a little bit of partial calculus, which I think you are quite competent to do on your own, but you don't need to do on your own because I have done all the steps and written the steps explicitly. Once you thus obtain equation for 51, you see something disturbing. Had there been only the left hand side and the first term in the right hand of the equal sign, the equation would have looked the same as in frame S. But alas, we have the terms within curly brackets appearing in addition. What does it mean? These are nuisance terms. Since these are arising, we can say that this particular Maxwell's equation in this particular example is not invariant under Galilean transformations. And we don't need to go to bigger generalities. If one example proves to be a counter example. That is to say, if in one case the invariance does not hold, we cannot make any further statement about invariance. So the bottom line is that Newton's equations may be invariant under Galilean transformation, but Maxwell's equations are not. In other words, Newton's laws and Galilean transformations are consistent, but Maxwell's equations and Galilean transformation are inconsistent. If you look at the schematic diagram in the lower part of page 17, what does that mean? That means there is some inconsistency arising between Newton's laws and Maxwell's equations. Of course, Newton's laws within the domain of their applicability have been tested. Maxwell's equations within the domain of their applicability is quite well tested. It therefore means that Galilean transformation is perhaps the culprit. Therefore, one's job is to look for some modified version of Galilean transformation. And when we discussed Maxwell's equations, just to recall our existing knowledge, we made this observation, the observation that the rate of time flow in frame S and frame S prime is assumed to be the same in Galilean transformation, but the truth of this is extremely important in checking how Maxwell's equations look in another inertial frame. So when we try to re-examine Galilean transformation in terms of the inconsistency we have just seen, it is important to remember that the assertion that time flows identically in two frames may be suspect. This is what we will examine in the next lecture in some modified set of transformations, which we will identify as Lorentz transformations. And in the next lecture, we will see that at least in the example we are talking about, the inconsistency is removed. That is to say, this particular Maxwell's equation in this particular case is still invariant. Of course, that will still not be a justification of the transformation prescriptions. For that, we have to go back a few steps and finally arrive at Einstein's starting postulate in terms of which these transformations follow. Of course, it then will remain our task to see how Newtonian mechanics or simple particle kinematics changes under such transformations. So far, so good. We end the present lecture here. I'll see you again. Thank you.